Greetings. In the last video, we talked about the EKG and how there is a path of depolarization through the heart that causes the muscle cells to be stimulated and to contract together in a uniform way. Now, those contractions are there to change pressure, and we use pressure in order to change the flow of blood. So, what we're going to talk about next is this relationship between the volume, the contraction and the relaxation, the pressure, the resistance, or what is trying to keep the flow from happening, and flow, and how all of those things are designed to get flow to happen in the direction that we want. Okay, so flow is proportional to the difference in pressure between 2 points. That's what this top part of the equation is saying. F is flow. This thing that looks like a fish means is proportional to. And proportional just means that if this goes up, the thing it's proportional to goes up as well. If this goes down, the thing it's proportional to goes down as well. So flow is proportional to pressure. This triangle here is the Greek letter delta, which means difference. So delta P means the difference in pressure between two places. So let's stop a moment and see if we can make sense of what just this is saying. So this is telling us that if we have pressure in one place that's, say, a pressure of 10 what, who cares, and a pressure in another place is a pressure of 1, then that is going to cause flow. Flow is going to go from the high pressure to the low pressure. Now it's proportional, which means that this difference that we had was a difference of 9. But if this is a pressure of 100 and this is a pressure of 1, then the flow is going to be even greater because the difference in pressure between the two places is also greater. Okay, so that's the top part. The bottom part means that flow is inversely proportional to resistance. Now, it means proportional just like it did before, but resistance is in the denominator, so it's actually 1 over R. So it's the inverse of resistance. So we would read this as flow is inversely proportional to resistance. Resistance means anything that's trying to block flow. So this is sort of obvious logic here that if resistance to flow goes up, then flow is going to go down. I mean, if you do something to try to stop something, then it should have that effect. If we take the resistance away, if resistance goes down, then flow goes up. And we're going to see this kind of relationship over and over this semester in A and P as we're moving fluids and air and all kinds of stuff. Okay. Oh, I said that part. So to get a sense of what this means, an intuitive sense, I'll go back to blocking this. I want you to imagine that we're squeezing a tube of toothpaste. So when you squeeze it, you make the pressure inside the tube of toothpaste higher than the pressure that's outside of the tube, which means that you're going to get a flow of toothpaste. The harder you squeeze, the more toothpaste is going to come out. And if you put your finger over the end of the tube of toothpaste and you try to squeeze, now we're increasing resistance, then flow is going to go down. All right, same thing with the heart. Let's take another example here. And this time we're going to look at the volume and how the contraction or making the volume smaller or the relaxation and making the volume bigger changes the pressure, which changes the flow. So in this example, we've got someone with a syringe and they're pushing the plunger down. As they push the plunger down, it's making the space inside the syringe smaller. It's decreasing the volume. It's not unlike what we're going to see with the heart when it contracts and it makes the space inside the ventricle smaller. Now you may be thinking, yeah, but the air is allowed out. Yeah, and it's true. But what's happening is that as the volume gets smaller, the pressure goes up. right? We're being squeezed tighter. And as the pressure becomes higher here than out here, that's what causes the flow. We don't see a big pressure difference because we allow the air to come out as we're pushing the syringe down. But if you put your finger over the end and pushed the plunger down, then and measured the pressure inside, it would be getting much higher. Okay. I think I said everything I wanted to there. So let's look at the opposite scenario. Now we are pulling the plunger out. We are increasing the volume. By increasing the volume, we decrease the pressure. Now this pressure is lower than the pressure outside, and so air flows in. It moves down its pressure gradient. Okay, in either case, if we put our fingertip over this opening and covered it completely or partially, we would be increasing resistance and we would make it so that less air was able to flow in or out of these syringes. Okay, the ventricles work the same basic way. In order to eject blood, the ventricles contract. When they contract, they're squeezing in, they're decreasing the volume, or the space of the ventricles, which means they're increasing the pressure inside the ventricles. And when the pressure in the ventricles becomes higher than the pressure in the arteries, it pushes the valves open and the blood flows from the ventricles to the arteries. To fill with blood, the ventricles do the opposite. They relax, and as they relax, the volume or the space inside the ventricles becomes larger. That decreases the pressure in the ventricles, and when it becomes lower than the pressure in the atria, the valves open and the blood flows from high pressure to low pressure. Okay, so let's add the valves. Valves are operated by changes in pressure, and they only open in one direction. So if we have a valve between chamber 1 and chamber 2, if the pressure in this chamber is higher than this one, the valve opens and we get flow from high pressure to low pressure. But if the pressure is higher in this chamber than in this one, then the valve closes and prevents the flow from high pressure to low pressure. So valves are kind of like doors with no pull handles. Right? They only open in one direction, and they can only be opened by pushing because there's no handle to pull. So it has to be higher pressure on the correct side. For this poor kid that can't get into the building, what's really needed is someone on the other side to push the door open. Okay, so let's look at how this happens with valves in the heart. Now, we're mostly focusing on the ventricles here because they do the biggest changes in pressure. So in this particular moment, the ventricles are relaxing. The volume increases, the pressure becomes lower than the pressure in the atria. The AV valve opens, or valves open, and the blood flows from the atria to the ventricles. Okay. This is actually called ventricular filling, and we're going to talk more about that soon. Now, in the next thing that happens is that the ventricles begin contracting. And as they begin contracting, they're making the volume inside smaller, which means that the pressure is becoming greater. When the pressure becomes greater than the pressure in the atria, so the blood is trying to get from the ventricles back to the atria, it pushes the valves closed. Right? So the AV valves close and the blood can't go backwards. Then what happens is that the ventricles continue contracting. The volume continues to get smaller. The pressure continues to get greater until the pressure in the ventricles is higher than the pressure in the atria. In the arteries. At this point, the semilunar valves are pushed open. Right, there's this valve and there's this valve, are pushed open and the blood flows from high pressure to low pressure in the arteries. This is ventricular ejection. Then the ventricles begin to relax. As the volume expands in the ventricles, the pressure decreases. It becomes lower than the pressure in the great arteries, and the blood wants to get back into the ventricles where there's plenty of space, but it can't because the semilunar valves slam closed. All right, let's look at this again. All right, so what I've got here is 3 chambers just represented by squares. We've got the atrium, which is always very low pressure, the ventricle, which has pressure that fluctuates a lot, and the pressure in the great artery, so either the pulmonary arteries or the aorta, that's usually quite high. In between the atrium and the ventricle is the AV valve. In between the ventricle and the great artery is the semilunar valve. All right, so at the point that we're looking at this, the ventricle is fully relaxed, so it has a super low pressure. This pressure is lower than the pressure in the atrium, which means that the blood will flow from atrium to ventricle because the AV valve opens in this direction. Now, when the ventricle begins to contract, this pressure starts to increase. When the pressure in the ventricle becomes higher than the pressure in the atrium, the blood wants to flow from high to low pressure, but the AV valve does not open in that direction. It stays closed in that direction. And so right now, there is no flow of blood. As the ventricle continues to contract, the pressure increases even more. It's still not able to open the AV valve, but now it's greater than the pressure in the great artery that it's next to. So the semilunar valve is pushed open and the blood can flow from high to low pressure, ventricular ejection. Then, when the ventricles begin to relax, the pressure starts to drop. The pressure becomes lower than the pressure in the great artery, so the blood now wants to go from the artery to the ventricle, but the semilunar valve does not allow that to happen. It's closed, and so at this moment there is no flow of blood. All right, let's look at this in a slightly different way. All right. So here we're looking at pressure, and we're looking at pressure over time. Now, the pressure in the atria and in the arteries is fairly constant. So I'm going to represent those with straight lines. Pressure in the atria is always low. Pressure in the arteries is always high. Yes, they actually do fluctuate, but this works. Ventricular pressure, on the other hand, fluctuates dramatically. Sometimes it's higher than the highest pressure. Sometimes it's lower than the lowest pressure. And it's the relationship between the ventricular pressure and the pressure in the arteries or in the atria that makes the valves operate and the blood flow. Okay, so let's look here. Whenever ventricular pressure is higher than the pressure in the arteries, that means that the blood can flow from the ventricle to the artery. Flow will always occur from the highest line to the line that's lower than that, from high to low pressure. In order for that blood to flow, the semilunar valve had to open. So as the pressure's increasing here in the ventricles, the moment that it becomes higher than the pressure in the great artery, that's when the semilunar valve opens. And for the entire time that the pressure stays higher, blood is coming out of the ventricles into the great artery. Okay, now the ventricles begin to relax, the pressure is starting to decrease, and the moment that ventricular pressure becomes lower than the pressure in the arteries, the blood wants to go from the arteries to the ventricles. But the semilunar valves close, and that prevents the backflow of blood. Now, that means that we've got no blood flow because right now the semilunar valve is closed, so the blood can't come backwards, but the pressure in the ventricles is still higher than the pressure in the atria, so that valve is also closed. As soon as the ventricle relaxes enough that the pressure drops below the pressure in the atrium, now the blood can flow from the atrium to the ventricle, which is allowed. the atrioventricular valve opens, and the entire time that the ventricular pressure is down here, blood is flowing into the ventricles. Now, somewhere around here, the ventricles start to contract again, and pressure starts to go up. As soon as the pressure in the ventricles becomes higher than the pressure in the atrium, the blood wants to go from the ventricle to the atrium. So the atrioventricular valve closes and there's no blood flowing here. So if we look at this diagram, every time the ventricular pressure is higher than the arteries, that it's above this range, the blood is flowing out. Every time it's lower than the atria, the blood is flowing in. And every time we're in between, there is no blood flow. The other thing to notice here is that the events that occur when these lines intersect up here involve the semilunar valves because it's between the artery and the ventricle. And the valves that are down here at the bottom are the atrioventricular valves, which are the ones between the ventricle and the atria. Okay, one more way to look at this. All right, so this graph is looking at the volume of blood in the ventricle. All right, so we're actually measuring it in mils or liters or whatever. Mils makes more sense. And on this side is the pressure in the ventricle. So as the ventricle contracts, the pressure should go up. As the ventricle relaxes, the pressure will go down. As the ventricle fills, the volume of blood will go up. As the ventricle empties, the volume of blood will go down. Okay, so let's start here. At this first point, where the volume of blood in the ventricle is at its lowest and pressure is at its lowest, that means that the blood is flowing from the from the atrium to the ventricle. So we can see the volume of blood increasing. Now the ventricle is going to begin to contract, and when it does, it's going to cause the AV valve to close. As soon as the valve closes, then the pressure is going to start building inside the ventricle, but it's not high enough to push the blood out yet. So what happens as the pressure continues to increase is that it causes the semilunar valve to open. This allows the blood to leave the ventricle, so volume's dropping down. And then the ventricle begins to relax, and so the pressure starts to drop. That closes the semilunar valve, and now the pressure decreases until the AV valve opens, and we start the process all over again. Okay, so hopefully one or more of those ways of explaining the relationship between pressure and valves and flow and paying attention to when the valves open and close and when pressure increases or decreases, that's starting to make sense.